Okay, I'm going to try to do this as quick as possible and as painless as possible. Point of inflection is, by definition, is where the concavity changes from positive to negative or vice versa. Okay, so to find one, the process would be to find where the double derivative is equal to 0 or undefined. Okay, if it's the double derivative is not equal to 0 or undefined, it's going to allow us to tell the concavity of the function. If the double derivative is a positive value, you'll see a function that is concave up. If you have the double derivative is negative, you'll see it's concave down. A function that looks like this will have areas where the function changes its concavity. So in this region right here, it's concave down. It's bowed down. It's frowning, whatever. It's concave down. Right about here, you'll notice that it's changing its concavity. Now it's bowing up. Then right around here, it starts concaving down again. So you have three places where you have concavity. Concave up, concave down, and concave up again. So in order for us to determine those features, we need that double derivative. So let's start with things that you'll see, information they'll provide. One thing they will provide you with is the graph of the double derivative. And here's an illustration of what they can ask you. Let's give you this B, and this is A. Now, if I want to ask you where the points of inflection are, or where it's concave up or concave down, I need the double derivative. So first I want to check where the double derivative is 0 or undefined. This is not the same as a critical point. This is on the double derivative, so don't get those confused. I see that it's a 0 at A and B. So what I want to do is now break it up into its intervals so I can see what the concavities are. So from negative infinity to A to B, and then B to infinity. If I pick a value between negative infinity and A that's in here, I have a value that's negative. Between A and B, I have a positive, and between B and infinity, like up here, I have a positive value. Hence, for this function, f has point of inflection at x equals a only, because b didn't change its values. It went from positive to positive, hence it's not a change in concavity. Here we have a change in concavity. It went from negative to positive. Okay, so looking at a function or the function's double derivative, something like 5x, x minus 1, x minus 3 square. Again, I want to ask you the question, points of inflection for f. So if I want the points of inflection, I need the concavities. So I'm going to set this double derivative equal to 0. If I do that, I get 5x equals 0, x equals 0, x minus 1 equals 0, x equals 1, and x minus 3 squared equals 0, x equals 3. So there's 3 points of possible points of inflection. Now, they're not inflections till we see there's change. So I'm going to set up my intervals to check concavities. Now, of course, I'm checking for concavity, so I'm looking at the double derivative. I'm looking up here, and I'm saying, okay, if I plug in a value like -1, which would be in this region, I get a negative, and remember, this is squared here, So no matter what, it's always positive. So I get a negative, negative, that's positive. Hence, this region is a positive. So therefore, it's concave up the whole time in that region between negative infinity and 0. I mean, just 0 or 1, I'll plug in a number. I get a positive, I get a negative, and again, I get a positive. Hence, I have a negative, so therefore, your function is concave down. And then from 1 to 3 again, I pick a number like 2, I get a positive, I get a positive, I get a positive, hence that's positive, concave up. And then finally, if I pick a number like 4, I get a positive, I get a positive, I get a positive, it's concave up. So I know this function is concave up from negative infinity to 0, 1 to infinity. The question here, though, is what are the points of inflection? The points of inflection are when the concavity changes. Hence, my points of inflection are at x equals 0 and 1. Now, I can't actually ask for the point because I would need a y, and I don't give you the function to find the y. Hence, I can only tell you where the points of inflection are located at. Now, let's change information. Let's go with, what if I give you the derivative? And let's look at a picture or a graph. Now there's the graph of the derivative. And I'm going to label these points A, here's B, C, D, E. Okay, so if I want points of inflection, then what I'm going to do is I'm going to look at slopes. Why? Because the double derivative is slope of the derivative. So if I look at the graph, from here to here, it's increasing. So right there is the first time I see a double derivative equal to 0 at B. Now here in this region here, it's the function's decreasing, the slope is negative, and then right here we have another change, and that occurs at C. And then we have the function going up, and then it stops and it goes back up again. Again, here I don't see any change, so only time I see a change is from here to here. So are points B and C points of inflection? Yes, they're both points of inflection. Why? Because if you look at your intervals now, the slope was positive, or the double derivative was positive here, negative here, and positive here. So both of those are changing signs. Change signs, change signs. So B to C are both points of inflection. If I give you a function, the function information I give you is an equation like this one. This is going to be tedious, so bear with me. So if I want points of inflection for the function, I would like to take the derivative of this to get the double. And this one's going to be fun. Remember this, we haven't seen each other in so long. This is a fig E. So the derivative of that would be 1/3 x to the negative 2/3 x minus 4 plus x to the 1/3 times 1. Now before I get into setting this equal to 0 or undefined, I want to make sure that it's a single fraction. So I'm going to move this down to the bottom with the 3. So I've got x minus 4 at the top, 3 at the bottom. X to the 2/3 was a negative power, so I moved to the bottom. And then this x to the 1/3 is at the top. Now, I still want this to be a single fraction, so that means I need a common denominator. So I'm going to multiply this by 3x to the 2/3. Now that looks ugly, and you need to calm your giblets down, because this ain't that bad. It kind of comes out in the wash here if you pay attention. So you got your common denominator. Copying the top of that one, and here it looks complicated, but it really isn't. So plus 3. If you take x to the 1/3 times x to the 2/3, you get x to the 1 power. How pretty that is. Okay. Now this is still my double derivative, and I have it being 4x minus 4 over 3x to the 2/3. Okay. Now, double derivative, I need it to be undefined or 0. So that means I need to take it, set it equal to 0, which means set the top equal to 0, which gives you x is 1. So there's a potential point of inflection. But I also have to set the denominator equals 0, because that's where it's undefined. All right. So I'm not done yet, because those could be points of inflection, but the problem is you have to do your intervals. So let's move down here. So I go, keep in mind, right here is the double derivative. And I'm going to do its intervals from negative infinity to 0, 0 to 1, 1 to infinity. And I'll pick some values for my double. Pick a negative. Now, look at this real quickly right there. I mean, I would not worry about that 2/3 power, because it's really a root of 3, and you're squaring it. And anytime you square something, you get a positive number. So no matter what, this denominator here, this denominator is always positive. So I really only have to worry about the top. How beautiful that is. Pick a number like -1. Would be in this region here. -1 gives you -4 minus 4 is a negative number. So that tells me the function is concave down. From 0 to 1, a half. 4 times a half, subtract 4 is a negative number. So it's concave down. Notice if I hadn't checked my intervals, I would have assumed x equals 0 as a point of inflection. But hello, it didn't change its concavity, so no point of inflection. But here, if you pick a number like in this region here, you pick 3, you get a positive number over a positive number is positive, so concave up. So my answer is I have 1 point of inflection at x equals 1. Okay. Now, if I give you the function, you're going to have to take the derivative twice, which can be quite annoying. But in the process, we can find different values and determine slopes. And there's many other values for the double derivative, and I'm going to get to that right now. One thing is, when we do extremes, remember here the key word is extreme. You take its derivative. Your process is what? Find crit points, endpoints, intervals, and then values, y values, if you need them. So if I wanted to find the extremes on using the first derivative, using this first derivative test, which we've always done it. It's nothing new. It's not new. I'm going to take the derivative, and I get 9x squared minus 27, sorry. And I'm going to set that equal to 0. Solving that out, you're going to get x equals the square root of 3 and negative square root of 3. So step 1 is crit points, and I have them. Step 2 is endpoints, D and E. There aren't any. Next step is intervals. Your intervals would be from negative infinity, negative radical 3, negative radical 3 to radical 3, and so on. And now here's where we're going to change things up here. And I'll explain to you why. Right now, we know that we could take the derivative and plug it into my derivative, which is located, I want my derivative, and it's located right here. I prefer that be in factored form, but right now let's not sweat that out too much. I'm going to pick a number like -10. If I take 10 and I square it times 9, subtract 27, I'm going to get a positive number. And in this region here, if I pick 0, I get a negative number. So it's increasing. The function now decreases. Oops. Decreases. And then if I pick a number over here like 10 over here in this region, 10, I get a positive number. So I have this function that's increasing, decreasing, and increasing, which tells us we have a local extreme and a local max here. And here, I've got a local min. Again, step 4 is the y values. And if x equals negative radical 3, I plug this into the original function, which is not going to be pretty, but I'll show you the plug-in. And I figured that whatever that is, and I have my maximum value of which would be here. This is my maximum value, and this is where it's located at. I can do the same thing with the local min. Now, let me just make a little observation here. What we're going to do is we're going to use another tool. Instead of intervals, remember your steps are crypt points, endpoints, intervals, then y values. What I'm going to do is I'm going to change this up just a tad, because sometimes it's a little bit easier. I'm going to use the second derivative test, which means I'm going to go step 1. I'm going to do my crits. I still need to know where those maxes and mins occur, and that's always going to be at a crit. 2, I'm going to do my ends, because again, that's where my extremes could occur. Now 3, here's where we get changed. Here's the big change. I am now going to use the concavity to tell me if it's a max or a min. Here's why. If a curve is concave up at a crit point, this is a picture of a concave down. If it's concave down, I can see that it is a maximum value. See how it's concave down and that's a max? That's a crit point right here at this value. Right here is a crit point. It's concave down, therefore that has to be a max. Same way with the if I have a crit point right there, here's a crit point. Right there is a crit point. If I look at that, I have a concave up. Therefore, it's a minimum value. So concave down yields a maximum value. A concave up region gives me a minimum value. So let's look at this exact same illustration here. Same equation. We already established crits. We established our crits were at x equals negative radical 3 and radical 3. We established no ends. Now, step 3 would be, I can use my intervals. However, here I'm going to take the double derivative because I'm going to check its concavity. So I believe, if I'm not mistaken, the derivative was 9x squared minus 27. So my double would be 18x. I like this because it's quick and easy for me to determine. Because now all I do is take my crit points, x equals negative radical 3, and that tells me my double derivative has to be a negative number. If it's a negative number, then my function has to be concave down. Therefore, it's x equals negative radical 3 is a concave down. See, I have to draw pictures. I'm not that intelligent. Concave down, it's got to be a max. And then I pick the other crit point, and if I use my double derivative test, I see that it's a positive number, because all I have to do is plug this in here, and I get a positive number. Therefore, since it's concave up, I have x equals radical 3 is where I would find my min. Okay, that's it. Please make sure you keep up with the work, and I'll see you mañana.